starting with this lecture here, what we're going to do is we're going to go through a series of functions. We already covered linear functions, but we're going to start with absolute values, get to power functions, polynomial functions, rational functions, and all this. And we're going to start studying the behavior of these things so we can understand what these functions actually do and what the graphs look like. And okay, so let's first make the absolute value function, define it as a piecewise function, and hopefully you'll remember how these work, where we're going to say if x is less than 0, in other words, if it's negative, we'll change the sign of it. That makes it positive, right? And if x is greater than or equal to 0, we'll leave it alone, so it's just x. So we have two cases. We're either going to change the sign or not. We're going to change the sign when it's negative. Okay, so the way this looks then is that the right-hand side of this graph looks just like a line, f at x equals x. Then this other part looks just like f at x equals negative x, and that's what you expect. One of the characteristics of this thing is that it comes to a sharp point at 0, 0.
Will it always be at the end?
Excuse me?
No.
No. Now we talked about translations and transformations with a absolute value function, that if we use the absolute value of x as f at x, we can move it around, and we can always kind of rely on this particular point to kind of tell us where to start, really. So if we're going to move it h units, this minus h is to the right, and then k is up, and depending on the sign it can move down and around and all over the place. So we can have a lot of functions that are absolute value function based that are simply translations of the function that we started with, the toolkit function of absolute value of x. Okay, so here's a little bit of a review, and perhaps it's a different way to think of it for many of you, that if we look at the absolute value of x, okay, think of this as x minus h and take the absolute value of that. You might want to think about this as the distance from x to h. If I were to take a number line and figure out what's the distance between 5 and 3, I would take 5 minus 3 and get the distance there. But in fact, we don't have to use one first, the larger one before the smaller one. We just take the difference between the two and take the absolute value. That way we'll always get a positive number, and distances are always positive, right? Just like when I measure a table, it would be 48 inches measuring it from left to right. It would still be 48 inches measuring it the other way, right to left, I guess, if that's the opposite of what I just said. Okay, so when we have an equation in an inequality, what we're really talking about, if this is the difference from x to 2, we want it to be less than 1. Okay, so hopefully this has a little bit a different physical meaning than just that equation up there, that we're looking at this number here, 2. X is a certain distance from 2, and it's going to be less than 1. And so here we have the set of numbers that are between 1 and 3. And so we actually solve this because it has to be within a range as an and, because both of these equations have to work out. So when we solve it, we see x is between 1 and 3. All right, so whenever you have a less than sign, it's always an and. Okay, you try this one. Make a graph of that. So this should only be a minute's work. Okay, so let's look at this. This is an or, right, because it's greater than. And so we make two equations out of it. We just take the absolute value, sign off of 1, and then we do the same for this side, but then we turn around the inequality and make this side negative. So when we solve it, x has to be greater than 2, or it has to be less than negative 4. And so if we were to graph this, here we have negative 4 and 2. What's larger than that? So if we look at a distance of 3, there's a distance of 3 here, and here's a distance of 3 this way, like this. Okay, so we have a distance of 3 both ways. So the distance that we're measuring, the center of this difference is going to be -1. Okay, so this is the way it breaks down, where you have the difference between x and another value. In order to make this work, that suggests that we have 2 negatives. And so we have the distance from x to -1 is more than 3, is one way to look at this now. Okay, before I go off on that, let's look at the graph of this thing in a way that is more function oriented. So if my function, let me rearrange this, x plus 1 is greater than or equal to 3. Let's subtract 3 from both sides, and let me make this. So I have -3 is greater than or equal to 0. So I'm looking for a specific case. I'm looking for this expression to have a certain relationship with 0, in this case larger. All right, so let me take away the 0 here, and let me define a function, f at x, and have it equal to this. Okay, so remember from a couple charts ago, you should be able to figure out what this graph looks like, right? It looks like an absolute value, but it's going to be moved to the left 1 and down 3, right? So we'll look at this as 1, 2, 3, 4, 5. This is x. So if I go to the left 1 and down 3, -1 and -3. Here's my point, and I have a slope of 1. I haven't changed, I haven't stretched it at all. So I would expect that this thing goes up like this, and then when x is 0, we have -2, and so we'll go up like this, and this one will go up to, it'll be like this. So at -2, 3. If I put in a -4, what I get is -4 plus 1 is -3. Absolute value of -3 is 3, so I have 3 minus 3 equals 0. So notice the intercepts here, okay? So if I go back to this, what I'm really saying is, if it's like this, is when is this expression, when is it greater than 0? So an equivalent question would be, when is my function greater than 0? Well, if I were to graph this using x as a number line now, I would be right here. Okay, so notice that everything, when y is above 0, that's my condition that this is greater than 0, or this distance is greater than 3. All right, so we have two kind of related concepts here. Number one is, how do we solve the inequality with one variable? But we can take this, and by putting everything on one side and having this equal to 0, if we make a function, we can look at the behavior of this over all values of x's and just decide, well, we want it bigger than 0. So it's these tails are bigger than 0, so our interval that we're looking at is like this. So your textbook makes a pretty big point of this. Okay, he talks about, you know, interpreting absolute values as a function and relocating it and things of that sort. So I think you have all the elements that's covered in that whole section. But the whole section is a little wordier than probably even my lecture, which tends to be wordy. So go ahead and read it. You'll find a few more subtle points, but this is kind of the point that they're making, is looking at the absolute value and how it relocates around. absolute value is going to be very useful for us as we get into limits of, or as we get into concepts in calculus. So study that section pretty carefully. Okay, so moving on from absolute value, now this is the next section in the book, and we're going to talk about power functions. Now, a function that is of this form, where f of x equals x to some power, that's a power function. It's different than an exponential function. An exponential function looks like this. They're similar, but not exactly the same, where a is a constant and you put in whatever value of x to get your function. This is a Math 14 kind of deal, okay? So you'll get that next semester. We're going to be dealing, though, with power functions, which are really the basis of polynomials. Okay, so that's what I just said. And this one, power functions includes our toolkit function for x squared and also for x cubed. So we're looking at those kinds of functions in general now. So I made a graph, and I put in all the power functions up to, well, numbers that were small integers. And so you see from this green one, we have x squared, just a nice parabola. And then this light blue one here is x cubed. Okay, and you'll notice one thing about it is that they're swinging up, but what happens is x cubed is a little farther this way than x squared. At 1, anything, or 1 to any power is 1, so all of these curves combine here. And then, if you can see the light blue one and the green one, that the light blue one increases much faster than the green one, and you would expect that. If you have x equals 2, x cubed is 8, while x squared is just 4. So we have some difference in behavior here, and I can go ahead and label some of these. This purple one is x to the 4th. This, what do you call that? That's purple too, but kind of a burgundy-ish. And then I'll just, exhaust the rest of these. So all the way up to this x to the 8th. Now it has the same kind of down and up that this x squared has, but as the numbers increase, it tends to flatten out a bit. The odd numbers, of course, retain the negative sign when x is less than 0, so these come from the lower left to the upper right, but they do the same kind of thing, where when you have x to the 7th, that comes up steeper than x cubed, and it flattens out, and then it goes. So we have basically this kind of flattening. You can imagine that if x is enormous, like maybe 100,000 or something like that, we would get almost something that looks like a bucket. Okay, it would be very fast down to 0, and then going up to 1, and very fast through 1, and up. So we get this general flattening. Okay, so when we have even exponents, as x gets bigger, x increases, f at x increases. And when you have values of x less than 0, as x decreases, f at x increases, right? So we have that, think of a parabola. As x decreases below 0, f at x increases. Now for odd exponents, the positive behavior is similar. As x goes up, f at x increases. But then as it goes down, f at x also decreases. So it gets to a larger magnitude negative number, but a negative 5 is less than a negative 3. So we have to be careful about how we talk about large negative numbers. Large negative numbers are close to 0. Small negative numbers are large magnitude, -10, -20, kind of numbers. Okay, so then in general, even, and odd. Now when we assemble different kinds of functions, remember this kind of behavior, and remember that the more flat it is, the higher the exponent. So something like this is, fairly round, so you expect that your exponent is relatively low. One of the things that it just occurred to me that maybe I should go back to look at this. If I were to plot f of x equals x to the 0, x to the 0, so long as it's not 0, 0 to the 0 power, or I should say x to the first. Now, here it's just equal to x, so here's an odd number power function, right, because we have 1. This thing is just going to look like that. So it even follows the general behavior of an odd function. Okay, the one that I started with, the x to the 0, is basically always 1, and so you do have a disconnect there where it's just a horizontal line, except 0 to the 0 is not defined. That's just as undefined as division by 0. But you see how even x to the first kind of generalizes in this pattern. Actually, I can draw it on board with this thing. That's pretty cool. Doesn't show up on my iPad, though. Anyway. Okay, so we'll go on. Enough of the toys. Okay, so the exponent increases, it widens the flat spot. Okay, so now we have polynomial functions. That's power functions. Fairly straightforward, simple function. We could put a coefficient in front of that, and the coefficient does what it does with any function. It either stretches it or shrinks it. And if you think about what happens when you put the coefficient in front of the x versus in front of the function, it really only changes by a factor of the degree of the function. So what is a stretch one way is a shrinkage the other way. Okay, so a polynomial function now, we can look at it as a sum of power functions. And so we'll take it in this order where we have a to the 0, a to the 1, or a sub 1, a sub 2, x squared. And so if you look at this, this is x to the first, and you can even think of this as x to the 0 power. That would be just a 1. So we normally think of a constant as just not having an x because x doesn't matter in there. So this can go all the way up to any number that we want. We can have hundreds of terms or whatever, but from a practical standpoint, we rarely get more than just a few dozen terms. Now this is probably backwards from the way that you're used to writing it, and there's two ways to write it. Generally, you either write it with the exponent in increasing order, or you do it in decreasing order. Decreasing order basically shows what the degree is, but increasing order, for those of you that are going to take Math 38, you'll be taking a section of calculus in infinite sequences in series, where this goes on infinitely long, and so it's more convenient to write it from the lower powers to the higher powers. Okay, so if I take any polynomial, we call the individual pieces of this thing a term. And the term includes the negative sign. So we're always going to look at this as the sum of terms. Some of the terms can be negative. Okay, so we retain that. So this is a 4-term polynomial. Now, we look at the degree of the polynomial as the degree of the highest term. So we have, since we have a 3x to the 4th, we call this a 4th degree polynomial. Now notice we don't have an x squared in here. And that's okay, you don't need every term. You still call the degree of the term by the highest power. So this could be just 3x to the 4th plus 1, and we'd still have a 4th degree polynomial. And the reason why we do that is that the long-term behavior of a polynomial is really dominated by the highest degree. Okay, so when we go out to many thousands, instead of just sticking close to 0, we'll find that the difference between this and any other fourth degree polynomial that has different terms in there is not going to be that great. So the long-term behavior is going to be dictated by the degree with the highest term. Okay, and we also call this the leading term, and of course the polynomial degree. And the 3 is known as the leading coefficient. So when you have a polynomial with a leading coefficient, what that's talking about is the coefficient of the leading term or the term with the highest degree. And of course, if we don't have a number there, if it's just x to the 4th, the leading coefficient is 1, right? You always have an implied 1 there. If it's a 0, well, you don't have that degree. For example, an equivalent polynomial would be 0x to the 5th, but we don't call it a 5th degree polynomial because that doesn't enter into the computation. And just remember, it always includes the negative sign. The way we're going to be handling things, it's important to consider that the negative sign is part of the coefficient, not part of the definition of the power function, or of the sum of the power functions. Okay, so let's look at some polynomial behavior. What I said earlier, the long-run behavior follows the long-run behavior of the leading term. So again, if I'm being repetitious here, but in the long term, that means when x is really, really big or really, really small, this is what the function will look like. It'll look very similar to 3x cubed, and there will be only very minor differences. Now, one of the ways that we can notate this is we're going to start using this arrow here, and that the way you can read this as x increases to infinity, f at x increases to infinity. As x decreases, gosh, I'm still writing. I've got to keep my finger away from the green dots. But anyway, as x decreases to negative infinity, f at x decreases to negative infinity. So you read that arrow as either increasing or decreasing, or you can think of it as it goes to infinity, or sometimes we'll have a number in here. We can say as x goes to the number 1, and there we're implying that it can go either from increase to 1 or decrease to 1. But as x tends to that number, that's the way we'll notate that. Okay, now the short-run behavior. By short-run, what I mean is localized behavior where things are kind of in the middle. I mean, it's usually around 0, but we can see that, as we translate a graph, we can move that, the intercepts anywhere we want, depending on how we treat x. If we, add or subtract a number, we can move it left or right. So the short-run behavior, when you're asking about that, you're really asking about things like the intercepts. And so the y-intercept of this polynomial function is just when x equals 0, right? Think of the graph. This isn't the graph, but on an xy graph, when x equals 0, that's when the function will cross through the y-axis. So the y-intercept is when x equals 0. Here, this is really easy to evaluate because all these terms drop out and you're just looking at the constant term. So the x-intercepts are a little bit more difficult to compute, and that's a wide, kind of a rich subject into itself is root finding. Finding where x equals, when y equals 0, where does it cross the x-axis? And so when we have 0 equals this, that's not a trivial question, right? I mean, if it's a quadratic equation, you can use the quadratic formula. Third degree, you're going to try and factor this first in order to find some solutions, but you may have to only approximate them. There may not be a solution. But if I am able to factor it, And so this is the way that this factors, okay, we won't talk about right now how to factor it, but just assume this is right, and you can check it by saying, okay, the -1 times -3 is 3, times 2 is 6, so the last term works, and the leading coefficients of all these, 3 times 1 times 1 is 3. So you can always check the first and the last terms for seeing if the factoring at least is reasonable. It may not be right. So in order to solve for this, where does the x-intercepts occur? Well, since we have it factored, one of these factors has to be 0 for this whole thing to be 0. So we have three different possibilities. We can have x equals 1/3, x equals 3, and x equals -2, and those will be the x-intercepts. Okay, so that's when y equals 0. The function will cross through the.
Do it cross all three of these?
I'm sorry?
Do it cross through all three of these, like, on the same graph?
Yeah.
So we like up and down?
Exactly. We'll get to building that too. Okay, so here's a polynomial function, just what you're suggesting. This thing can go up and down and, through and through. Since it's a function, there will only be ever one y-intercept, right? Because when x equals 0, y can only, or the function can only equal one value, and that's just wherever it happens to cross. It's not true with the x-axis. It can cross through it many times. And so the long-term behavior of an odd power, remember it behaves like the leading term. And so if we have, that was a third-degree polynomial, right? We'll just go back to the, it's a third-degree polynomial. So we're going to expect that the long-run behavior is as this thing goes to negative infinity, f at x goes down to negative infinity. As f at x goes to infinity, f at x goes to infinity. So it goes from the lower left to the upper right. Okay, so it behaves like an odd power. The short-run behavior changes a little bit. Yes?
Does that have to do with the leading coefficient being positive?
Yes. If the leading coefficient is negative, you're right. It goes the opposite way because we're going to flip the whole graph. We're going to invert the whole graph.
Okay.
Now, the maximum number of roots is the polynomial degree. So that third degree polynomial that I showed you, we actually found 3 roots, right? And I don't know if I graphed this exactly right, but it's going to go through the x-axis a maximum of 3 times. Now, it doesn't have to go through 3 times. In fact, we can have a third degree polynomial do something like this. Okay, so it looks like it could if we added something or subtracted something to it, but it really only, what we're really talking about here is the maximum number of roots, and that is, that's the degree. Now, the maximum number of turning points is one less than the polynomial degree. So a turning point is where it changes direction. Okay, that's what I'll, not very mathematically precise, define it that way. So if I look at a third degree polynomial, it can change direction exactly twice. So it has a turning point, 1, 2. It doesn't have to have that many. Like if you just look at x cubed, it just goes up, flattens out, and goes up again. So it really doesn't even have a turning point. It's always increasing. But if you have other terms in there, the maximum number of times it can turn around is like this. So here's one that doesn't have, it only has 1 root, but it has 2 turning points. And so you could surmise that this graph here can have a degree of no less than 3 because there's 2 turning points. Okay, so that's part of understanding what a graph is. You look at it, you say, 3 roots. It may be a cubic equation. 2 turning points, add 1 to 2, and you get 3. So there's 2 pieces of evidence that you have at least a third degree polynomial. It could be a higher degree, but it cannot be lower. You can't make this graph with an x squared kind of a deal or a linear function. Okay, so that's polynomial functions. And so we'll go on if anybody has any questions. Actually, we should try a few just as a matter of practice here. Okay, so let's take a little closer look at one particular kind of polynomial function, quadratic functions. So we can tell those two things about the in transformation form. The vertex is going to be at h and k, because remember, h moves it left or right by h units, k moves it up and down, and that place that it, if we have just our toolkit function, the vertex is at 0, 0, and since we're moving the places around h and k, we can quickly see that we're going to get the vertex at h and k. Okay, so if we extend it all out, you can see here's the first term, here's the second term, and then h squared plus k is the third term. Now you can work this out when you have real numbers, and it looks a lot simpler than the stuff that I'm putting in, but it does give us some more information here. Negative 2ah is b, and h squared plus k is c. Okay, so this is just basically undoing this kind of factoring. If we have b is negative 2ah, and we're going to divide both sides by 2a, what we get is negative b over 2a equals h. Now h is how much we're moving it back and forth. That's also the axis of symmetry. So when x equals h is a really good axis of symmetry, and that's negative b over 2a. So if I take a polynomial, any polynomial, let's say minus 5 equals f of x. So the first thing that I'll know about graphing this thing is that if I take negative 6 over 2 times a, which is 3, this is going to be negative 1. The first thing that I'll notice about it is that at negative 1, I'll have the axis of symmetry. Okay? So that's where it's going to go from a back and forth standpoint. And that's from this form. This is the ax squared plus bx plus c. Now if I just put negative 1 in here, and so I'll get 3 times negative 1 squared plus 6 times negative 1 minus 5 equals, this is going to be 3 minus 6 is negative 3 minus 5, and this is negative 8, right? So then I know that at negative 8, I have my vertex. All right, so a very quick way to find where the vertex is that we don't necessarily have to put it in this form, although we could. We can get it from this ax squared plus bx plus c form by finding the axis of symmetry and then taking that value and sticking it back into the function, and that'll tell us what the k value is. Okay, so here's what I'm doing. I take this h value and I stick it in here, and this is the coordinate pair that describes where the location of my vertex. So in this case, it's here. Okay, let me do another example. Find the vertex of this function. All right, so the first thing I'm going to do is take minus b over 2a, and that is negative 12 over 6, which is negative 2, so that's my axis of symmetry. And then I'll stick that negative 2 back into my function, and I can evaluate that to be 12 minus 24 minus 4 is negative 16. So my vertex is going to be at negative 2 and negative 16. Okay?
Can you leave that for a second?
Yeah, sure.
Is this lecture gonna be online?
Yeah.
Have the video and stuff?
Yeah, and I think I am recording. Yeah, I am recording, so the recording will be on there. Okay? Okay, we found H, we found K, we know A is the same coefficient as the leading coefficient, so we can actually put it in this form right here. Okay, it just zips right there. Now, the traditional way of doing this is doing something called completing the square. And how many of you remember how to complete the square? Just kind of vague, right? Okay, we'll have some exercises then in completing the square, and I'll talk about that on Monday as well, because completing the square is going to really be helpful when you're doing substitutions in calculus. You can put things in a certain form by completing the square. Okay, let me see what else I have here. Okay,